Today we will begin performance monitoring of energy utilities in textile industry. Performance monitoring of energy in textile industry. Major energy utilities of textile industries are boilers and steam system, thermic fluid heater, compressed air systems, and humidification system. Here in detail we will read about thermic fluid heater and humidification system. Today we are going to cover thermic fluid heater. What is thermic fluid? Thermic fluid is petroleum based fluid examples are furnace oil, light diesel oil, heavy fuel oil, and Hindustan Petroleum HP markets thermic fluid under brand name Therm 500 and Therm 600. Therm 500 has maximum bulk oil temperature up to 290 degrees centigrade, and Therm 600 has maximum bulk temperature 320 degrees centigrade. This is about thermic fluid. Now we come to thermic fluid heater. Let us see its use first. Thermic fluid heater provide thermal energy for high temperature operation such as drying of fabric in stentor after dyeing operation in wet processing, In a stanter or dryer, hot air of 140 to 200 degrees centigrade is required. This may be for purpose maybe to remove chemically held water from the textiles by evaporation or physically or chemically set the textile material. Now let us see working principle of thermic fluid heater. There are four stages. First is combustion, combustion chamber generates heat. Second is heat transfer. This heat generated from combustion is transferred to the thermic fluid flowing in coils or pipes surrounding the combustion area. Here, cold thermic fluid will enter and it will be get heated in combustion area. And third is circulation. Heated fluid thermic fluid is pumped to the heat exchanger where it transfers its heat to the process, and lastly it returns cooled fluid returns to the heater for reheat. Thus we see that this is a closed cycle operation, and as we know the efficiency of a closed cycle operation is always greater than steam boiler. for the same purpose. So we can see what happened. We have till now we have seen thermic fluid like furnace oil, light diesel oil, high speed diesel, etc. This thermic fluid is acting as a heat carrier. I am explaining what we have seen in the working principle, just repeating those things. This thermic fluid is heated up in heater and circulated through the user equipment, and it transfers heat for process through a heat exchanger, and finally fluid returns to the heater. So this is a 4-step process we have seen. First is combustion, then heat transfer, then circulation, and finally return. What are the advantages of thermic fluid heater? First is it has higher efficiency as compared to steam boiler. Reason is obvious, because it is a closed loop operation. Second important thing is non pressurized system operation. Temperature around 250 degrees centigrade can be achieved through non-pressurized system operation, and the same operation in steam system will require 40 kgf per centimeter square steam, that is pressure of 40 bar, and here in thermic fluid heater it is non-pressurized system operation at 250 degrees centigrade, and this is for boiler. So it is advantage here, no extra pressure is required. And third important thing is automatic control settings. We can maintain desired temperature for desired time. We have just seen the operating principle of thermic fluid heaters and its advantages over steam boiler. Now coming to efficiency. Thermic fluid heater efficiency is equal to heat output divided by heat input, simple one, multiplied by 100 for percentage. And now let us see both these terms. Heat input kilocalorie per hour, this is the unit. This is equal to fuel firing rate, how many fuel is getting fired per hour, and gross calorific value of fuel, this is in kilocalorie per kg. Thus we have found out heat input. This is the formula that will be used for heat input, and for heat output, heat output is mass flow rate of thermic fluid kg per hour into specific heat capacity of fluid its unit will be kilocalorie per kg per degree centigrade, and temperature difference in degree centigrade. So its input will be, its unit will be kilocalorie per hour. Now we have heat output, heat input, and so we can find out thermic fluid heat efficiency. With this information, we can find out thermic fluid efficiency. Now we will see its application through an example. Here we have a question. Just I am increasing its font so that you can see it clearly. The question is, in a textile mill, a thermic fluid heater of 15 lakh kilocalorie per hour capacity is meeting process heat requirements. Here the capacity of fluid heater is given. The observed parameters of thermic fluid heater are circulation rate is given 100 meter cube per hour. This is volume per hour. We have outlet temperature of fluid and return temperature of fluid. We can find out delta T here, 270 minus 256 degree centigrade. A specific heat of fluid Cp is given here. Density of fluid has been given here. Using this volume per hour and density, we can find out mass flow rate. Mass flow rate is equal to volume per hour into density. So we can find out for finding heat output, we will need mass flow rate. We can find out mass flow rate very easily here. A specific heat of fluid is already given here and temperature difference is already given here. So we can find out heat output very easily. Then we have been given coal consumption 300 kg per hour, that is, this is fuel firing rate, and gross calorific value of coal is also given. So we will find out heat input also. Now we are in a position of finding heat output and heat input both. First question is saying what is the percentage loading of the thermic fluid heater? We can find out it very easily. First of all, find out heat output. Heat output is equal to mass flow rate into a specific heat capacity of fluid and temperature difference. Mass flow rate is given volume per hour 100 meter cube per hour into density 830 kg per meter cube. We have found out mass flow rate. A specific heat capacity given is 0.55 in the question here. Kilocalorie per kg per degree centigrade, and temperature difference, that is also given here, 270 minus 256. When we multiply it, we will find out this comes out to be 6,39,100 kilocalorie per hour. We have found out heat output percentage loading is equal to heat output divided by capacity of thermic fluid heater. In the very beginning, in the question, it has been capacity has been given 15 lakh kilocalorie per hour. In the question itself, you can see this is the capacity, 15 lakh kilocalorie per hour capacity. So put these two values, kilocalorie per hour divided by 15 lakh kilocalorie per hour multiplied by 100 for percentage. This comes out to be 42.60%. This second question, second part is what is the existing thermal efficiency? For thermal efficiency, we have already found out heat output is equal to 6,39,100 kilocalorie per hour. We have to find heat input. Heat input is fuel firing rate, that has been given 300 kg per hour, and gross calorific value of coal, that has been given 3500 kilocalorie per kg. This comes out to be 10 lakh 50,000 kilocalorie per hour. So we have both heat output and heat input. Efficiency of the heater is equal to heat output by heat input. This will come out to be 6,39,100 divided by 10,50,000. Units are kilocalorie per hour. Kilocalorie per hour. We will multiply by 100 percentage efficiency. This will come out to be 60.86 percentage. We have found out efficiency, and the third part of the question says the management is proposing to add a 5 chamber, each chamber 1 lakh kilocalorie per hour duty to the heater. Will it be able to take load? Existing load is this much, 6,39,000. This is existing heat load. Apart from that, management wants to introduce 5 heat chamber of 1 lakh kilocalorie per hour capacity. So this is additional heat load. So total heat duty with new stator loading is equal to this is existing plus 5 lakh, these two components, kilocalorie per hour. This comes out to be this much. And as the capacity of thermic fluid heater is 15 lakh kilocalorie per hour, it will be able to take load. The answer will be yes, it will be able to take load. Just for the sake of completeness, I want to make it clear that heat output or heat duty, just I will define heat duty. Heat duty is total amount of thermal energy that needs to be transferred to or from a system like heat exchanger, to achieve a desired process condition. Temperature, desired process condition means desired temperature and pressure. In this problem, what we have done? We have found out heat output and heat input that gave us thermal efficiency, and heat output gave us percentage loading, because we know the capacity of thermic fluid heater in this textile mill. And then it was said that 5 new chamber is being proposed of 1 lakh kilocalorie per hour duty. Will that be feasible? Will it be able to take load? Answer is yes, because the total load after adding this proposed load is below 15 lakh kilocalorie per hour capacity. So it is feasible. Thus, in this lecture, we have seen the performance of thermic fluid heater. In the next lecture, we will come across humidification system. Till then, thank you. This lecture was presented by Fazari Energy Auditor classes. Watching.